All right, so today we're not actually going to solve a math problem. Instead, we're going to dissect the genius behind one. We're going to treat a standard high school trigonometry chapter like a brilliant piece of design, like a hidden blueprint for how to teach pretty much any abstract idea. Let's dive in. You know, a great lesson never starts with boring formulas. It starts with a question that feels, well, impossible. The textbook kicks things off by asking, how would you find the height of the Qutb Minar without actually measuring it? And boom! Suddenly, it's not a math problem anymore. It's a mystery. By posing this question, the book creates this immediate, powerful need to find an answer.
The answer, of course, is trigonometry. But the real genius here isn't the math itself. It's the design of the lesson. The textbook follows this deliberate four-step blueprint to make the impossible feel totally achievable. And this first step is all about setting the stage.
And this right here, this is the core principle of great teaching. Before you get a single definition, before you see any formulas, you get a reason to care. The book makes a promise. Hey, stick with us and we'll give you the tools to solve problems that seem completely out of reach. It's all about motivation before memorization.
So it lays out these really concrete challenges right at the beginning. It's not saying, hey, learn trigonometry. It's saying, learn how to measure a tower, figure out how wide a river is, or track a hot air balloon. The whole chapter is basically positioned as a toolbox for a mission. You're not just learning math, you're gearing up for an adventure.
Okay, so now that we're motivated, the chapter starts to fill that toolbox. And this is the second step in the blueprint, moving from the why to the what. It's time to define the fundamental language and the tools we're going to need to build our solutions.
The design starts with simple language. Every right triangle has three key sides, but they're all relative to a specific angle. You've got the hypotenuse, the opposite, and the adjacent. And notice how opposite and adjacent completely change depending on your point of view. This isn't just a definition. It's a really strategic move to build a clear foundation before any numbers get involved. So with the language all said, the book introduces just three main tools: sine, cosine, and tangent. And they're just simple ratios, a way to compare the lengths of the sides we just defined. By starting with only three, the textbook makes the whole thing feel way more manageable. These are the absolute bedrock of our new toolbox. And here's where it gets really clever. Instead of just throwing three more confusing names at you, the book presents the next set of tools, cosecant, secant, and cotangent, as simple flips of the first three. It's a brilliant little trick. You don't have to memorize 6 different things, you just memorize 3, and then you learn their 3 inverses. So much easier.
Okay, this is a super critical moment. A student might be thinking, hang on, if I have a tiny little triangle and a huge one, won't the side lengths be totally different? Won't that mess up the ratio? The textbook sees this confusion coming from a mile away and tackles it head on.
And the answer is no! As long as the angle, in this case angle A, stays the same, the size of the triangle doesn't matter one bit. The sides all scale up proportionally, which means their ratio stays exactly the same. The sine of angle A is 1/2 in the small triangle, and guess what? It's 1/2 in the big one too. It's a constant.
And this is the big conceptual breakthrough, that aha moment. These ratios aren't a property of some specific triangle. They're a universal property of the angle itself. That's the idea that unlocks everything, and it's the whole reason a universal table of these values can even exist in the first place.
So we have our tools, and we know they're consistent. This brings us to the third step in the textbook's blueprint, calibrating those tools. It's time to move from these abstract definitions to some concrete numbers for a few very common angles. And here it is, the table that so many of us spent hours trying to memorize. But the genius here is that the book doesn't just hand it to you and say, learn this. It actually derives every single value using simple geometry. It proves these numbers aren't just random, they're a product of pure logic. Let's just focus on one value for a second. The sine of 30 degrees is 1/2. It's a simple, clean ratio. Now just hold that number in your head. Because now, get this, the cosine of 60 degrees is also 1/2. Huh? Is that just a coincidence? The textbook doesn't explain it yet, but it's planting a seed, a little bit of subtle foreshadowing that we're definitely going to come back to.
So we've gone from a concrete problem to definitions to calculations, and now we reach the fourth and final step of the blueprint, abstraction. This section isn't about finding a number. It's about understanding the deep, hidden relationships between the tools themselves.
First up, a really important definition. An identity isn't like a normal equation. You know, sine A equals 1/2 is an equation. It's only true for a specific angle. But an identity is a statement that is true for any angle you can possibly plug into it. It's like a fundamental law of this whole system.
And this might be the most brilliant move in the entire chapter. It reveals that the complicated-looking identities we're about to see all come from one place that every single student already knows by heart, the Pythagorean theorem. It's a masterful way to connect this new, kind of scary topic to old, familiar ground.
The method is just pure elegance. You take the Pythagorean theorem, and you just divide the whole thing by each of the three sides squared, one by one. Divide by the hypotenuse squared, you get the first identity. By the adjacent squared, you get the second, and the opposite, the third. 3 fundamental truths, all born from one simple act. Just beautiful.
And now for a fascinating little twist. When you compare the official textbook to the kind of revision tools that students actually use, you find something's missing. It's like there's a ghost haunting the curriculum, a topic that's been removed but whose presence is still totally felt.
The official textbook flows from ratios to specific angles and then to identities. But if you look at how students often study for a test, you'll see this extra step right in the middle, complementary angles. Turns out it's a topic that was officially removed from the syllabus, to lighten the load, but it hasn't quite disappeared.
And this ghost topic explains that coincidence we saw earlier. The reason sine of 30 degrees equals cosine of 60 degrees is because 30 and 60 are complementary angles. They add up to 90. The rule sine A equals cosine 90 minus A was part of that section that got removed. So even though the rule itself is gone, the evidence of it is baked right into that table of values.
So when you finally zoom out, you see the entire blueprint. And it's just a masterclass in scaffolding knowledge. Step 1. Start with a concrete, tangible problem. Step 2. Define the basic tools and language. Step 3. Calibrate those tools with specific numbers. And only then, at the very end, Step 4. Move to pure abstraction. This logical flow is exactly what makes learning stick. And that brings us to our final thought. This was never really just about math, was it? It was about the art of explanation. And it kind of makes you wonder, what other elegant blueprints for learning are hiding in plain sight in the subjects you think you already have all figured out? Thanks for tuning in.